So, we will be continuing with looking at generalized Jacobians, or we will generalize it and then review the pseudo inverse thing again, because when it is introduced suddenly, it is sometimes a little too much. Okay, now we looked at Jacobian control the previous day in very broad terms, and I can do the that I can do interpolation using this mode. Now, suppose I have decided on going along this path, and then I have discretized and I have picked up point 1, point 2 and point 3. Well, there will be more points, point 4 and point 5 along this path. And let us say that we somehow are at point 1 right now, because we have done Jacobian control and we have converged. Okay. So, from this point, when I want to go to point 2, so I will calculate delta x1 and delta y1, okay, as these two values. So, I am going to take delta x1, delta y1 and shove it into this matrix, which is capital X1. So, as standard nomenclature, if you have theta 1, theta 2, theta 3, all small thetas, then you represent the matrix version of that by using the capital X1. So, this denotes the position at point 1 in the Cartesian coordinate system. So, I just take delta x1 and delta y1, cascade them together one below the other. So, I get delta x1. And so, we know that if I now want to find out what is the delta thetas that I think I need to move from point 1 to point 2, then I will get that by using Jacobian inverse multiplied with delta x1. Now, this Jacobian inverse is something that I will calculate at point 1. Now, what I then do is I have this delta theta 1 which I am calculating, and then I add this delta theta 1 to the theta 1 values at the point 1, and I will get a theta 2 prime. Now, this theta, I am calling this theta 2 prime because when I add up theta 1 and I add the delta theta suggested by the Jacobian control technique, I am not going to land up at point 2. I am going to land up at some other point out here, which I am calling 2 prime. Okay. So, this is where I land up. Now, once I am sitting here and I want to go to point 3, next step I am going to calculate my delta x2 and my delta y2. Okay. Now, please note that I do not calculate delta x2 as this value. I use from the position where I will reach, not my target position. So, I have reached here, so I am calculating delta x2 as this and delta y2 as this. Okay. Not this and this, not these two values. This is worth noting. So, essentially delta x2 is then the vector x3 minus the vector x2 prime. Then you repeat this process, and the Jacobian is now computed at this point 2 prime. Okay. You do not compute the Jacobian at point 2 because you have not reached there. You do not know the theta values at 2. Okay. And it is not worth trying to find out the theta values at 2. So, you do that and then you will go on to the next position. So, you find out a delta theta 2 matrix using this, you add it to theta 2 prime, and you will end up at this point 3 prime. Okay. So, this is just minor detail, but it is significant detail looking into the process. And now you note that if you just want to stop at 3, then you just run from this point 3 prime, you just run Jacobian control a couple of times, maybe you'll end up here, and you'll converge to 3. So if you want to go exactly to that point, then you just run from this point, you'll run a couple of more times Jacobian control, and you'll come very close to this. So that's how I can come to this point 1, or very close to point 1. Okay. So this is just adding some more detail to the material covered yesterday. Okay. And we did look at that if we now have a 3-link manipulator and we are interested in the Jacobian, it then becomes of a different form, which is longer than it is wider. So how do we handle this? We simply then, instead of finding the Jacobian inverse, well, then you use this form, you use A plus, which is A transpose into AA transpose minus 1. Okay, you use this form of it. So that gives you a solution. Okay. So in this case, AA transpose will be a 2 by 2 matrix, so you can invert it pretty easily. I mean, there is no difficulty in inverting it. And then you multiply it with A transpose and you get a matrix which is then the Jacobian inverse, and you can proceed with the control strategy exactly as you have in the earlier class. Okay. Now, I want to revisit this portion on singular value decomposition. Now, singular value decomposition is a very general tool. I just talked about it in the previous class to kind of let it settle in. It is used in a wide variety of problems, and including spectral analysis, and you can do this singular value decomposition not only using vectors, but you can do that using functions also. Okay, so it's more general than what I am presenting it as. We are only interested in matrices, right? And essentially this process of writing a matrix in this form U sigma V transpose, right? Now this is called the singular value decomposition of A, because these matrices all are rather in some unique form. Okay. For example, this matrix contains solely the eigenvalues or square root of the eigenvalues in the diagonal form. Okay. And similarly U, the V matrix consists of the corresponding eigenvectors, right? And well, so you can find only so many eigenvectors. If the matrix is longer than that, what do you do for those remaining ones? You can fill it up by using Gram-Schmidt process, and then you can find UR by using this formula, because you already identify VR, and then you define this sigma R inverse, and then you can find UR. So you can compute it uniquely, and you can show that in general this process is simpler than doing it the brute force way in which you invert a matrix, especially if the matrix is large. 2 by 2 matrix is not a problem, right? You can invert it quite easily. But if you are pivoting and inverting, and there are some other stability issues which are handled very nicely when you are going through the singular value decomposition route. Plus, okay, so if you want to know about Gram-Schmidt, usually a course in orthogonalization, in a course in linear algebra you should have covered it. And so now once you have identified the V, sigma and the U matrix, A plus is given by this combined formula, and the useful part of it immediately is that if you take this, then you can define what is called the right inverse and the left inverse, and for the Jacobian case which I showed earlier, we were interested in this matrix. Okay. And this is not a very difficult formula to remember, because if a matrix is say 3 by 2, right, then it is a 2 by 2 matrix which is invertible. The 3 by 3 will never be invertible, okay, because the rank is 2. So that you get by doing AA transpose, and now if you land up with a 2 by 2 matrix, after you take the inverse, you can only multiply, you can pre-multiply it with A transpose, you cannot multiply it with A. right, or you cannot post multiply with. So it's fairly unique. It's not so difficult to remember. So, and the other interesting thing is that this method allows you to generalize solving of linear equations and orthogonal equations, and which is a useful tool in life overall. So it answers two questions. If you have 6 equations, 6 unknowns, you'll get 6 exact solutions, 6 solutions, unique, right, if rank is 6. Now if you have 4 variables and 6 equations, you do not have a solution, quote unquote, that's what you are told. But there is nothing called you do not have a solution, right. So you find out what is the best solution. Now best solution perhaps is the one which minimizes the error Ax minus b. So you start with Ax is equal to b, you move the b over here, so you get Ax minus b is equal to 0. So you cannot solve for Ax minus b equal to 0, at least you solve for Ax minus b equal to as small a value as possible. So that is what you get if you have more equations than you have solutions. Now if you have more variables, then you have number of equations, then what is the best thing you can do? There are many solutions. So you just find the solution which has the smallest norm of the vector. Okay, so suppose you have to move from position A to position B, so there are many solutions that you can find. So you move delta theta 1 by 30, this by 20, this by 70. Then other solution to find this is 40, this is 30, this is 90. Which is the solution that you prefer? So it is logical to say that find the solution which causes a cumulative least movement at each joint. So these kind of solutions come if you have more variables than you have equations. And so this is what it says, and this set here gives you the additional solutions which you can manipulate, called the null solutions, to do other useful criteria other than what is supposed by the equations. Now so today for the remaining portion I want to look at the MATLAB symbolic tool and just show you how you would go through and calculate and work on the robotics tool. So this is a very simple example. I think it's best just run in MATLAB. So let me escape from this. Okay, oh, it's already running. Very nice. What is this? Okay. Now where is the editor? Okay, so we can simply define theta. Now this looks like a so I'm telling it that every time you encounter the character string theta, right, you treat it as a symbolic variable. Okay, that's all I'm telling it. That's all fine. It's a theta is equal to theta, that is not much. So now we say what is equal to okay, sin theta square nothing very interesting, right? It just reflects that. But now simplify. So it knows your class 9, class 8, class 9 trigonometry? Huh? 10th? No. You have not regressed, right? We used to do it in class 8 and now I'm told everything is 1 year later. So maybe class 9, right? Definitely class 9. Class 8? No. Cos square theta plus sin square theta? Man. So what do you guys do in class 8? So MATLAB is at least at class 8 level. Anyway, so let's look at something more interesting. Open recent places, courseware. Okay. Okay. So this is a little bit more complex. So
can you maximize this?
Can I maximize? Certainly maximize, but the font size will not increase. Okay, I'll tell you what I'll do. I'll just okay, no, I have it in my this thing. Let me switch back to this. I can increase the zoom here. Okay, this is perhaps the best way of doing it. Okay, now you can see it. Better? Okay, so oh, okay. This is the correct one. Okay, so in this case, I am defining theta. So I am basically trying to multiply these two matrices together, 4x4 matrices together. I might have to do it for various applications. And so theta is equal to symbolic theta, phi is equal to the symbolic form of pH. Then I define the Z matrix for theta. So I just write similarly cos theta and then minus sin theta 0 0 semicolon, and these three dots are continuation, right? So it means it continues on to the next line, sin theta cos theta 0 0, so on and so forth. As I define this matrix, then I define this matrix rotation of x with P, which is this, again in the symbolic form. Okay. Now for the product, I simply need to get, just multiply it like a regular matrix and ask for the symbolic form of that. Okay, then we'll do some simplifications. So let's copy this and now put it into the command window. See what it does. Okay, so you get the full trace. So it defines the Rod-Z matrix like this. Okay, so it gives Rod-Z rotation about the z axis by theta in this form, and then rotation about the x axis by phi in this form, and then it gives you the product very neatly in this form. Okay. So it's very nice, right? And you could have cheated on your first year homework, right? If you have used this properly. You guys didn't use mathematics also? No? You've heard about it? Achha, never used it. But MATLAB you use, so this is actually quite convenient. So it's very easy to program, and then you can. So now at some stage you can at this stage you can say theta is equal to this value, right? Including pi by 3 and so on and so forth.
So how is that done?
How is?
How do we put theta is equal to something, because it's a symbolic class?
You just assign a value to it. So this is essentially, I have taken a 3-link manipulator, and define the length of the first link as unit 3, second as unit 2 and last as unit 1, so that they are not just all 1. And so I have defined the first 3 as pi by 3 and then 10 star pi by 3, so on and so forth. Okay. You can also define as quote 30 and then you can take it forward also. And then so I just define theta 1, theta 1 2 and theta 1 2 3. Okay, this is very convenient for forming the Jacobian. So first term is length 1 star theta 1 minus length 2 star theta 1 2 and then minus length 3 star theta 1 2 3, and then so on and so forth. So you go through these definitions. Okay. So you define the full Jacobian. Now after that, once you have this definition of the Jacobian, now this is very interesting because essentially in successive steps when you are using the Jacobian, you just need to update your theta matrix and the rest of the computations are identical. So you can use it, put it in a loop also in MATLAB pretty much using this form. So now I said, okay, you please use the symbolic form of this Jacobian which is calculated, and then I multiply this Jacobian with the transpose of the Jacobian. I defined it to be symbolic so that it keeps all the terms together, does not mess around with it. And then I ask it to find out the eigenvalues and the eigenvectors, okay, of that. So I form the matrix D and then I invert D. So then the VR that I talked about gets defined as Jacobian transpose times U star D inverse. And then I simplify VR and finally see the well, I will show you the VR matrix which is right down here. So this is what happens. Okay. So it writes the Jacobian in this form. Okay. Now this form minus half into 3 into square root of half is minus half root 3 root 3 0. So this is the pretty form of that. And then the product of the two Jacobian, this is the pretty form of that. Okay. So it is behaving, right. So it works. So you can write pi and then it works, give specific values. And so what? Yeah, but it's in radians. So I do not know because now MATLAB also supports degrees. So there is sin d and cos d. I have never tried giving cos d with 30 as the parameter and seen whether it pops up square roots and things like that. That you can check and let me know whether it does it. I have usually always used the radian form. Old habits. So then you form U and then you form D. So you can see D is in this form. U is a little bit more complicated. Okay. And then you calculate the V. Okay. So which is 2 in this direction and 3 down. And finally you can find out what is the, so it is 2 in this direction and 3 down. So you need to still find out one more column of that. So that you can do very simply by taking the cross product, because the third one you want it to be a spanning set. So if you take just the cross product of these two vectors, it will give you the third vector. So I have used a cheap method of finding what is called the spanning set. But you cannot usually do that if your matrix is larger than that. If essentially it is 6 deep, then you cannot do a cross product, right? Then you have to use Gram-Schmidt to find the spanning set. So that you can look up. And finally, what I do is I check that what happens. So I told you that other than the eigenvectors that you get, if you get the remaining spanning set, they all consist of null vectors. So I am just checking whether the product of the Jacobian with this null vector that I generate, whether that is actually 0, and it does turn out to be 0. Okay. So, just a verification. So, with this, essentially you have tools to work on this problem, and what I have done is I have hopefully this is the last slide in the series. Yeah. Where is the net? Ah, now it comes. So, you can go and find out all about Gram-Schmidt process, Wikipedia, find up books on linear algebra. It is a very, very standard and very easy to use method. You can code it very easily, and it just uses dot products and subtractions of vectors. Okay, so it's quite easy to find out, and it's not a big problem. And the other thing I want you to do is point out that what I have done today is I have uploaded I shouldn't have done this, I will not be able to download this, but anyway. So, there are these two more exercises, one in DS transformation and one is in Jacobian plus pseudo, use of Jacobian plus pseudo inverse, where you can play around with it, look at the numbers, okay, and get comfortable with working with the Jacobian control. Okay. And when you solve these problems, think about the shorter methods of solving this problem. Okay. I mean, there are these brute force methods, you can do everything, but every step start to think that how can I do this faster? Where do I have a smaller set of steps? Okay, how can I compact my calculation? How can I do it faster? Okay, because well, that's the whole exercise. Okay, so you need to think a little bit. So please download them and have a work on it. Work on this system. Now, what I would have done normally after this is to get started on trying to derive the Jacobian for the general manipulators of the 3D manipulators. Now, the easy way of doing that, the very easy way of doing that is to simply take, do it the way it's been done here, right, which is you write out, like I've written expressions for Px and Py, right. I write expression for Px, Py, Pz of the end effector, and I start taking derivatives. Okay. The only thing is it will run into pages like this. And not only that, so you'll end up with a 6 by 6 matrix. Okay. And if I want to invert it, inverting a 6 by 6 matrix is not trivial. Okay. There are a lot of pivoting problem and error problems. So we will look at a method in which you can write down the Jacobian in a very, very compact and elegant form, but after we do quite a bit of some amount of mathematics relating to representations of line in space. Okay. And you will actually be able to invert even Jacobians of most common industrial manipulators in the closed form. So it's a 6 by 6 matrix which, by examining the rows and the columns, you can invert it in a closed form, so you can write expression in terms of sin theta, cosine of theta. Okay. And that makes it very convenient because then you can program that and you can use it for computations. Now, so I do not want to start on it today because I will not be here tomorrow and Friday. Okay. So we will start on that material on the following Tuesday.